In this video, we're going to look at sequences and their notation. We're going to define what a sequence is, explicit or closed formula. We're going to write the terms of the sequence defined by a recursive formula, and then we're also going to use a little factorial notation. So let's take a look at this example here. We have this video game company, and they're going to launch this new advertising campaign. Then they predict the number of online visits to their websites, or hits, will double each day. The model that they're using is 2 hits on the first day, 4 hits on the second day, 8 hits on the third day, and so on. If their model continues, how many hits will be there at the end of the month? Well, our input, or our domain of this sequence, is the natural numbers, 1, 2, 3, 4, 5. So this 6th day all the way up until if you have 30 days, your last input would be 30. So that is the domain. You're putting in these whole numbers, natural numbers, if you will, whole numbers not including 0, or the natural numbers 1, 2, 3 on up, or the positive integers not including 0. And then what comes out is multiples of 2. 2 to the 0, or 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and etc. Now, how do I figure that out? Well, there's a couple of ways to do it. The first way is doing it is it tells us that it's going to double each day. So I take 1 is my input and 2 comes out. I put in 2, so that knows I'm going to multiply 2 times 2 twice. So 2 times 2 actually once, but 2 times 2, 2 by itself twice. That gives me 4. I put in 3. That means it's 2 times 2 times 2, or 2 to the third. And then I have 4, and then I'd have 2 times 2 times 2, or times 2, which is 2 to the fourth. And so you'd see the pattern that way. This is a sequence. So one of the ways I could write this sequence is I could say a sub n is equal to 2 raised to the n. And that's one of the ways I could represent this sequence using sequence notation. And you're thinking, what is that? What is a sequence? Well, a sequence is a list of numbers that are ordered. It has a particular order. And the domain is a subset of the counting integers. In other words, they're the natural numbers. They're the whole numbers not including 0. They're the positive integers, so 1, 2, 3 on up. And so if we take a look at this, this is our sequence. This is one of the ways that we can represent the sequence. We'll use a curly bracket. We use a comma between each one of the terms, and then we use these 3 little dots that are called ellipses, and we use that to show that it's going to continue on indefinitely. And that would be assuming that this trend of 2 hits, or the doubling of the 2 hits each day, is going to continue forever. The first 5 terms of the sequence is 2, 4, 8, 16, and 32. And the way that we could note that is a sub 1, that a sub 1 indicates the first term, and that's 2. A sub 2 represents the second term, or 4. A sub 3 represents the third term, or the number 8. Now, here is the formal definition of a sequence. A sequence is a function whose domain is a set of positive integers. A finite sequence is a sequence whose domain consists of only the first n positive integers. So a finite one means that we have a certain set and it doesn't go on forever. The number in a sequence is called the term. The variable a, or you sometimes may see it as b, with a number subscript is to represent the term. So it's a replacement for the term. So a sub 3 is the third term. We call a sub 1 the first term, a sub 2 the second, and etc. A sub n is called the nth term, or the general term, or the explicit formula for the nth term. And a sequence that continues forever is an infinite sequence. So the question is, can we start with a sub naught? Well, not if we look at how we define it. A sub 1 is the first term of the sequence, and each one of those subscripts represent the inputs. So we always have the inputs. Well, we put in 1, which means a sub 1 would represent the first term, and the 1 would represent the input of 1. So can we start with 0, a sub 0? Not right at this moment. So what would be the next 3 terms of the video game example? What would be the nth term? Well, we kind of talked a little bit about what the nth term is, but let's give you the next 3 terms. We've got the 6th, or the 5th term. So a sub 6 would be 2 to the 6th, or 64. And then a to the 7th would be 2 to the 7th, and a to the 8th would be 2 to the 8th. And we talked about this a little bit earlier. The closed or explicit formula, the a sub n, when I see that, that's telling me the closed or explicit formula, which is 2 raised to the n. So if I want to go to the 10th term, I can jump right to the 10th term. So here's something for you to ponder. If I asked this to you in class, what would be an example of a finite and what would be an example of an infinite sequence? So just kind of think about that. So if we are given the explicit or closed formula, how do we find the terms? Well, we look to see where we should start. We usually start with n sub 1 because we would normally start with the first term. But say we wanted to jump with terms 7, 8, 9, and we might be able to just jump and do 7, 8, 9 as the inputs. On this one, they were asking me to find the first 4 terms. So in other words, what they're asking me to do is find a sub 1. So I'm going to put 1 into this closed formula. So I have negative 3 multiplied by 1 plus 8. This gives me negative 3 plus 8, which is 5. A sub 2 is negative 3 multiplied by 2 plus 8. So I have negative 6 plus 8, which is 2. A sub 3, and again, notice that where I have the input is 3, I'm going to replace in the closed or explicit formula, I'm going to replace that in with the number 3. So negative 3 multiplied by 3 plus 8. So this is going to give me negative 1. And then my last one, which is a sub 4, so I have negative 3 multiplied by 4 plus 8. This gives me negative 12 plus 8, which gives me negative 4. So my first 4 terms here would be the sequence that start out with 5, 2, negative 8, and negative 4. Now, since we are assuming we're going down forever, in this case it's decreasing. You can go in 5, 2, negative 1, negative 4 are my output, so it's decreasing. So that would be one way to represent the sequence, and I've got the first 4 terms. If we take a look at the next example, notice we're using d instead of a sub n, and that's totally fine. So if I want to find the first 4 terms, so d sub 1 is I'm going to do negative 1. Wherever I see n, I'm going to replace it with 1. So I have negative 1 raised to the 1, 1 raised to the 2, all divided by 1 plus 1. This is going to give me negative 1 raised to the 1 is negative 1, multiplied by 1 raised to the 2, which is 1, divided by 2, and so my first term is negative 1/2. D sub 2 is negative 1, the quantity squared, and then I have 2 raised to the 2, and then I have 2 plus 1 in the denominator. So now I have a positive, because negative multiplied by negative is a positive, and then 2 squared is 4 over 3. D sub 3 is negative 1 to the 3rd, 3 squared over 3 plus 1. So this is going to give me a negative 1 raised to the 3rd power is a negative 1 multiplied by 9. That's 3 squared. So I have negative 9 in the numerator, and then I have 4 in the denominator. And then my fourth and final term, d sub 4, would be negative 1 raised to the 4th, 4 squared over 4 plus 1. So this is going to give me a positive 16 over 5. And again, I can denote the sequence as a negative 1/2, comma 4/3, comma negative 9 over 4, 16 over 5, and etc. Now we would call this an alternating sequence because I'm alternating between a positive and a negative. So this is an alternating sequence. The next one I'm going to look at is C. Now, they're not giving me the way they're presenting this mathematically is they're not giving me a subscript. They're not telling me to use A or D. So I'm going to choose. I'm going to use A. So this is telling me where I want to start, and this is telling me where to end. But remember, I only want the first 4 terms. So A sub 1 would be equal to the natural log of 1 divided by 1. Well, the natural log of 1 is 0, so my first term is 0. A sub 2, it's a terrible looking 2, is equal to the natural log of 2, excuse me, sorry, divided by 2. And so that's about as good as I get. I'm going to leave it as the natural log of 2 divided by 2. My a sub 3 would be the natural log of 3 divided by 3. And my a sub 4 would equal the natural log of 4 divided by 4. That's about as good as it gets. And again, I got some issues with my pen here, so thanks for bearing with me. We talked a little bit about this. Our example here with b is called an alternating sequence. It changes from positive to negative or negative to positive each term. Each term switches and alternates. So how do we figure out how to write the sequence? If you're given an explicit formula with an alternating term, write the first n terms of the sequence and then substitute, then go back and substitute each value of n in there with n being 1, so a sub 1, and then pay attention to when you switch signs, and they will alternate. They literally will alternate. So what is a quick way to determine if your sequence is alternating? You just look at the signs. If it's negative then positive or positive then negative, we know it's an alternating sequence. So now we're going to write out the first 4 terms of the sequence. Now you can do one of 2 ways. You can just write the sequence and then determine whether or not it's positive, starts out positive and then goes negative, or if it starts out negative and goes positive and puts the appropriate sign. I personally just like to jump in and put in the n where it's appropriate and just figure out the sign as I go through the sequence. So my a sub 1, which is going to be negative times a negative 5 raised to the 1 minus 1. Well, 1 minus 1 is 0. Anything to the 0 power except for 0 is 0. So my first term is just 0. So that's not going to actually tell me whether or not my next term is negative or my next term is positive. So now I'm going to do a sub 2. And so I have negative 5 raised to the 2 minus 1. Well, 2 minus 1 is 1, so it's a negative 5. Negative 5 times that negative 1 out front gives me a positive 5. My next one would be a sub 3. And so my a sub 3 is going to be negative 5 raised to the 2, which is equal to a negative, it'll be a positive 25, and the negative out front will make this a negative 25. My a sub 4 will then equal a negative 5 raised to the 3rd power. So that would be a negative 125 multiplied by the negative 1 out front, which will give us a positive 125. So my sequence is 0, 5, 25, and then that should be negative 25, and then a positive 125. And then it just continues from there. Okay, let's take a look at the next example here. So for a sub 1, this is going to be equal to negative 10 raised to the 1, not n. So 10 raised to the 1, plus 1, which is going to give us negative 10 plus 1, which is negative 9. A sub 2 is going to be negative 10, quantity squared, plus 1. So this is going to be 100, a positive 100 plus 1, which is 101. My next term, which will be a sub 3, this is going to be equal to negative 10 raised to the 3rd power plus 1. So it's going to be 1,000, negative 1,000 plus 1. So this is going to be a negative 999. And then a sub 4 is going to be negative 10 raised to the 4th power plus 1. So this is going to give me a 10,000 plus 1, so 10,001. So this would be negative 9, which is a negative number, to a positive 101, to a negative 999, and then to a positive 10,001. And I know that the next term, of course, would be negative because that's the way it's alternating. And so my next term would be a negative, and I'm just going to write it like that, showing that it's going to continue on in that direction. So then now, how do we do a piecewise function, because sometimes we have piecewise functions. So if it's even, we choose this. If it's odd, we do this. So as we go through our a sub 1, a sub 2, a sub 3, we just decide whether or not we're going to use this first part or the first piece of the formula or the second part or the second piece of the formula. So we're going to start out with a sub 1. Starting out with a sub 1. Since 1 is odd, we're going to use the second piece, which is 3 raised to the 1 minus 1. And so our first term is going to be 3 to the 0, or just 1. A sub 2, since 2 is odd, 2 is even, we're going to use the first piece of the piecewise function. So we have negative 2 raised to the 2 minus 2. And so I'm going to have negative 2 raised to the 2 is a positive 4 minus 2, which gives me a positive 2. A sub 3, well, it's an odd. 3 is odd, so I'm now going to use the second piece of the piecewise. And so I'm going to have 3 raised to the 3 minus 1. So this is going to give me 9. And you can see that it just depends on whether or not my input is odd or even. Now, if we take a look at B, and I'll let you all finish the first example, I'm going to do the same thing with B, as I'm just going to get you started. On B, it's divisible by 4. So if the number that I put in is not divisible by 4, then I use the second piece. If it is divisible by 4, I use the first piece. A sub 1 is not divisible by 4. Divisible means that it's going to, when 4 divides into that number, I'm not going to have any remainder. Well, clearly when I take 1 and divide it by 4, I'm going to have a remainder, because 4 does not divide into 1. So that's how come I'm going to use the second piece. So I'm going to have 2 divided by 1, which is 2. And then a sub 2, again, 2 is not divisible by 4. So I have 2 divided by 2, which is 1. A sub 3, 3 is not divisible by 4, so it's it's going to be 2 divided by 3. And then 4 is finally divisible by 4, and so I get to use the first piece. This will be 2 multiplied by 4 plus 1, the quantity squared. So I have 8 plus 1, which is 9, squared is 81. And I would continue in that manner. What a recursive sequence is a sequence that depends on the previous term or previous terms. One of the most famous recursive is the Fibonacci. So Fibonacci sequence is a 1, a 2, a 3, a 5, and an 8, and etc. So this one depends on the first 2 terms. And so the way in which I got 2 is I added 1 plus 1. The way I've got 3 is I add 1 plus 2. The way I got 5 is adding 2 plus 3. The way I got 8 is I add 5 plus 8. And so my next term would be 8 plus 5. That's one of the most famous ones, Fibonacci. So the way in which I determine whether or not it is recursive is it's usually going to give me the first term or terms that I need for my sequence. And notice how my subscripts here, I have a sub n minus 1. So when I see a sub n minus 1, that means that it's asking me to use the previous term to find the current term. And so I know that that is a recursive sequence. And then this one here, this should be a sub n. I just want to say that this should be a sub n, then a sub n minus 1 minus 2n. And then in the denominator, it should be a sub n plus 1 plus 5. That's a typo on mine, so I just wanted to fix that for you. But let's go ahead and do the first one, and then we'll come back to the second one. So for the first one, I already know what my first term is. My first term is 9, so a sub 1 is equal to 9. A sub 2 is going to be 3 minus. A sub n minus 1 is asking me to use a sub 1, because I have the, let me back up a little bit, because this is kind of weird. So a sub 2 minus 1, it's terrible. A sub 2 minus 1, and then minus 20. So let's baby step through this. So 3 times a sub 1 minus 20. Well, a sub 1 happens to be 9, so it's 3 times 9 minus 20. 3 times 9 is 27 minus 20 is 7. So my second term is 7. Now let's do the next one. I have a sub 3. This is 3 times a sub 3 minus 1 minus 20. So this is 3 times a sub 2 minus 20. So this is 3 times a sub 2, which is 7, minus 20. And so this is going to be 21 minus 20, which is 1. A sub 4. This is going to be 3 times a sub 4 minus 1 minus 20. So this is going to be equal to 3 times a sub 3 minus 20. So this is going to be 3 times 1 minus 20. And so my sequence here is going to start out with 9, then 7, then 1. Oh, I didn't finish this. 3 minus 20 is negative 17. And then it's going to continue on from there. It's a recursive. So let's go ahead and go through this example B here. And knowing that this should be a sub n is equal to a sub n minus 1 minus 2n and a sub n minus 1 plus 5. Let's make that correct. A sub 1 is already given to us. This is equal to negative 4. A sub 2 is going to be a sub 1 minus 2 multiplied by 2 over a sub 1 plus 5. Because it's a sub n, which is 2, minus 1, which is 1. A sub 1 is 4. So I have 4 minus 4 over 4 plus 5, which is 0. A sub 3 is going to be my previous term, which is a sub 2, and that's 0, minus 2 multiplied by my n, which is 3, over 0 plus 5. So this one is going to be negative 6 over 5. My final one, which is a sub 4, because I only want the first 4, this is going to be negative 6/5 plus 2 times negative 6/5 all over negative 6/5 plus 5. Now, because I have fractions within fractions and I can't leave that, what I'm going to do is I'm going to just multiply the numerator. I'm going to multiply the numerator and the denominator by 5 to clear my fraction. And when I do that, I'm going to get negative 6 plus 2 times negative 6, all divided by negative 6 plus 25. And then I was able to clear that fraction nicely, and so I get negative 6 in the numerator and 19 in the denominator. And that is my fourth and final term. So, what is factorial? Well, factorial is kind of recursive. So if I see 5 factorial, that means I'm going to take 5 and multiply it by 4, multiply it by 3, multiply it by 2, multiply it by 1. So it always takes your highest number, so 5 factorial would be 5, 4, 3, 2, 1, all multiplied together. If I have 7 factorial, it'll be 7, 6, 5, 4, 3, 2, 1, all multiplied together. We have a couple of special cases. We say that 0 factorial is 1, and we say 1 factorial obviously is 1, because 1 times 1 is 1. So how do we do a sequence that is defined by factorial? Well, here's an example. If I have the sequence which is a sub n is equal to 5 to the n plus 2 factorial, then I put in 1. Wherever I see n, I put in 1, so I have 5 multiplied by 1. In the denominator, I have 1 plus 2 factorial, which is 3 factorial. So that becomes 3 times 2 times 1, which is 6 in the denominator. What about a sub 2? Well, then I have 4 factorial in the denominator, 4, 3, 2, 1, then 5 factorial, then 6 factorial, and then 7 factorial, and you can see how that goes. So if I'm just asked to evaluate factorials, that's all I'm asked to do. So if I'm asked to evaluate 6 factorial, this is 6 multiplied by 5, multiplied by 4, multiplied by 3, multiplied by 2, multiplied by 1. So to get my calculator out, I don't need a graphing one or anything. I can just multiply all these together. And I've got my calculator out. And so I'm going to get 6 times 5, which is 30. That multiplies by 4 times 3, which is 12, and that gets multiplied by 2. When I finally get done, I get 720. Now on part B here, I am going to just get that factorial down to where I can cancel. And what I mean by this is I'm going to write out the 12 factorial as 12 multiplied by 11, multiplied by 10, multiplied by 9, 8, 7, and then 6 factorial. And the reason I'm going to stop right there is because in the denominator I have a 6 factorial. This allows me to cancel those two as if they're not even there. That's just like saying 3 over 3 or 7 over 7 or 42 over 42 because that is the answer to everything. So then I would do 12 multiplied by 11 multiplied by 10 multiplied by 9 multiplied by 8 multiplied by 7. And I get, when I get totally done, I get 665,280. Still a pretty large number. Okay, so that's factorial. How do we determine the explicit formula if we're given a sequence? So that's a big question. How do we do that? Well, first of all, we want to see if there's any kind of pattern. Are they going up by the same number between? So am I adding the same thing to each number? Am I subtracting the same number each time? Am I dividing the same number each time? So that's what I'm going to do is I'm going to look to see whether or not I can do that. If it's a fraction, I typically will look at the numerator separate than the denominator. So I will look to say, hey, is my numerator doing something and is my denominator doing something? Now, if I'm asked for the explicit formula of the nth term, the first thing I'm going to do is do the easiest. Is the same number between terms being added? So between 60 and 40 is I've added 20 to it. And then here I've also added 20 to it. So I look, what's happening is that it looks like I'm adding 20 to each term. So what I think is happening is a sub n is going to be, let me see, if I have 1, if my a sub 1, so my a sub 1, if I put in 1, 40 has to come out. If I put in 2, 60 has to come out. If I put in 3, 80 has to come out. So I think what I've got is I think I have 20 plus 20 multiplied by n. Now let's check. If I put in 1, does 40 come out? Yeah, I've got 20 plus 20, which is 40. If I put in 2, does 60 come out? I have 20 plus 20 times 2, which is 40 plus 20 more is 60. Yeah, that seems to work out. So this is my explicit formula for the first one. Now let's take a look at the second one. Now what's happening on the second one is my first term a sub 1 is 1, a sub 2 is 2, a sub 3 is 4, a sub 4 is 8. So between the first two terms is 1, between the second two terms is 2, between the next two terms is 4, and then 8. So I don't have a consistent amount being added to each term, but it's kind of consistent. I'm adding 2, 4, 6, 8 each time. So I don't think I'm going to be able to do as easy as I did for that first one, but I know that I'm going up, like, I know that 2 to the 0 is 1. I know that 2 to the 1 is 2. 2 squared is 4. Oh, so it's kind of like doing 2 raised to the n power, but I do need to adjust for it. So I'm going to have a sub n. When I put in 1, 1 needs to come out. So in other words, I need 2 to the 0. So I have 2 to the n minus 1. I'm going to check this. If I put in 1, I have 1 minus 1, which is 0. 2 to the 0 is 1. Cool. That's my first term. If I put in 2. 2 minus 1 is 1. 2 to the 1 is 2. Let's see if we put in 3. So if I put in 3 right here, I have 3 minus 1, which is 2. 2 squared is 4. Cool. I think I have the right one. So I think this is my closed or explicit formula for B. Excuse me. So now let's take a look at C. Let me move all of this all up out of the way. Let's take a look at C. So as we take a look at C here, I have got these fractions. And like I said, if I have fractions, typically what I'm going to do is I am going to separate the numerator and denominator. So I'm going to rewrite this as 2 over 1. I'm going to make them all fractions. So I'm going to write it as 2 over 1. So if I look at my numerator, it's going 2, 4, 8, 16. Oh, that looks like it's raising my 2 to the n. Now I have a negative. It's a alternating sequence. And the way I do the alternating sequence is I know I'm going to have -1 raised to some power. If I need the first term to be negative, I'm going to raise it -1 to the n. If I need my first term here to be positive, then I'm going to write this as n plus 1, or maybe n minus 1. But if I have my first term as negative, which is this one, I'm going to write this as -1 to the n. So that takes care of that alternating part. Now, if I look at just the numerator, my numerator is 2, 4, 8, 16. Now, again, I'm not worrying about the alternating because I already took care of it. So my a sub n is going to be, so it looks like it's going up with 2 to the n. So it looks like I'm going up 2 to the n. So if I put in 1, I get 2. If I put in 2, I get 4. If I put in 3, I get 8. If I put in 4, I get 16. So that seems to be okay. Now, if I look at my denominator, again, I'm only going to focus in on the denominator, not the sign. I have 1, 3, 9, 27. Oh, these seem to be multiples of 3. Now, if you remember in my last example, I needed my first one to be 1, not 3 to the 1. I need to be 3 to the 0. And the way I do that is I'm going to write this as 3 to the n minus 1. And that will ensure that I have 3 to the 0 in the denominator, so my denominator will be 1 for the very first term. So that is that example. Let's take a look at my next example. And once again, I'm going to put this over 1. And my denominator actually is going to be the, oh, it's alternating too. So I have a sub n. Now, I want my first term to be positive, so I'm going to write it as -1 to the n plus 1. This will ensure that if I have 1 plus 1, I have -1 squared, which means it's going to be positive, and that will get my alternating. Now, in my denominator, I'm going to start by my denominator first. I have 1, 3, 5, 7, and I guess the next one would probably be 9. So what's happening is I'm going up each term by 2. So I need to have the first term to be +1. So when I put in 1, what'll come out when I put in 1 is 1. When I put in 2, 3 needs to come out. When I put in 3, 6 needs to come out. Oh, so this looks like it might be 2 to the n minus 1. So if I do 3 times 2, it's 6 minus 1 is 5. 2 times 4, which is 8 minus 1 is 7. Oh, yeah, so that's cool on that one. Now, the thing that's changing in the numerator is not the x part, it's actually the exponent. So let's focus on the exponent. The exponent is 1, 3, 5, so, oh, that's awesome. That means that I have x raised to the 2n minus 1 because it's going to match my denominator numbers. Now, notice I didn't worry about the x part, I just worried about the exponent. Now let's take a look at e here. Well, the thing about e is it's a mix of fractions and whole numbers. So let me rewrite this as 1 over 1, 1 over 1, 4 over 3, 2 over 1, and 16 over 5. Well, look, this is my third term. This one's my fourth term. So I think what I want to write, instead of writing 1 over 1 and 1 over 1 and 2 over 1, is I need to have those denominators go 1, 2, 3. So I'm going to rewrite this as 1 over 1, 2 over 2, which is still 1, 4 over 3. Now the next denominator I need to be 4. So if I multiply the numerator and denominator by 4, I get 8 over 4. Oh, sweet, that's nice, isn't it? And then I have 16 over 5. Now what this is going to do is it's going to allow me to focus in on the numerator and the denominator separately. So a sub n is equal to, well, let's look at the denominator. I have 1, 2, 3, 4, 5. Fifth term is 5. Fourth term is 4. Third term is 3. Second term is 2. First term is 1 in the denominator. So that's just n. That is lovely. Now the numerator we see, we've already seen it a couple of times. It's 1, 2, 4, 8, 16. So we know this is going to be 2 to the n minus 1. And that is that one. Now let's take a look at this example in which I have these sequences. Now the sequences here are presented a little bit different. The outputs are the numbers I'm going to focus in on, the 5, 7, 9, 11, and 13. The inputs would have been 1, 2, 3, 4, and 5. Now notice this is linear. So we're going to actually label this in the next video. we're going to call this an arithmetic sequence. So if it seems to be going up linearly, it's an arithmetic sequence. So my inputs are 1, 2, 3, 4, and 5. The sequence I'm going to focus in on are the numbers 5, 7, 9, 11, and 13. Now, I just said that this is a arithmetic because it's going up linearly, so it's like almost like right in a line, right? So if I put in 1, 5 comes out. If I put in 2, 7 comes out. So what my sequence then is a sub n is equal to. Now, if I were to draw a line, of course, this with sequences are not actually a line because my inputs are only the integers, the positive integers, 1, 2, 3 on up. But if I were to draw a line, I would actually draw the line, and it looks like it's going to cross at the intercept of 3. So 3 is like my initial number before I even start. I call it a naught. It's like, hey, this is the number that I'm going to use just to get us going. And then I notice that the slope of this line, and remember, it's not truly a line, it's just the dots. Looks like it's a slope of 2. So that is my sequence. Now, I can also tell you what the multiplier is because I'm going up 2 each time. So as I'm going up 2 each time, that's why that is 2n. Now, if I to get out 1, if I put in 1 and the only way to get 5 out if I'm going up 2 is I had to have had 3. And as I take a look at this last example. Now this example, if I were to draw this shape, which they're not, by the way, you do not actually draw them because we only put in integers, we don't connect the dots. It's actually an exponential shape. So this is an exponential type shape. So if I put in 1, 6 comes out. If I put in 2, 7 comes out. If I put in 3, 9 comes out. If I put in 4, 13 comes out. If I put in 5, 21 comes out. And then it continues on, of course, like that. So this looks more like an exponential. So if it's an exponential, or maybe even a quadratic, I got to figure out how if I go at 1, 6 comes out, and then I have 6, 7 comes out, and then 9. And so the first thing I'm going to do is I'm going to check, and this is plus 1, this is plus 2, this is plus 3, plus 4, plus 4, plus 4. And then this one looks like it's plus 8. Oh, so it's an exponential. So this goes back to exponential functions. Now remember, with exponential functions, we can have shifts left, right, up, and down. So what I think is happening is I have 2 plus 2 raised to some power. So I'm going to just go with 2 to the n. So if I put in 1, let's see if I have a starting number of 4. So if I do 4 plus 2 to the 1, that gives me 6. Squared. Well, 2 squared is 4. 4 plus 4 is 8. Well, that doesn't give me my second term. So it clearly cannot be 4 plus 2 to the n. So what could it be? Well, what about a recursive? What if I told you that a sub 1, what if I gave you the a sub 1 and I said a sub 1 is equal to 6? What if I said a sub 2 is a sub 1 plus 2 to the 1? Would that work? Actually, it'd need to be 2 to the 0. So let's do 2 to the 0. Would that work? Well, a sub 1 is 6, 2 to the 0 is 1. Let's do a sub 3. That's a sub 2 plus 2 to the 1. Is that going to work? So I have 7, because that's a sub 2, and this is 7. 7 plus 2 to the 1, oh, that's 9. So I think that might be it. So we have a recursive. So it's still kind of exponential part, because it's 2 to the raised to the, but I need to have the previous term. So my a sub n is going to be a sub n minus 1. I need to have this as part of my recursive, and then plus 2 raised to the n minus 1. That should be minus 2. So let's check a sub 4. A sub 4, remember this was 9, so I have my previous term, which is a sub 3, which is 9, plus 2 to the 4 minus 2, because it's n minus 2, which is going to give me 9 plus 4, which gives me 13. So that one works. Now let's do the last one. I I have a sub 5, which is the 13. That's the previous term. A sub n, which is the previous term. 2 raised to the 5 minus 2. So I have 13 plus 8, and that does indeed give me my 21. So there I found a formula that is recursive. It's kind of exponential because I have 2 raised to the power. And basically what this is an exponential function that has been shifted up. And it also has a movement to the right. So there you have it. That's the video for this one.